In this video, we're going to look at critical values and what they mean and how to find them. So first, what is a critical value? It's just a z-score that has a specific use. It splits up a normal curve from a certain percent of the data from the other percent of the data. So here's an example of what it looks like. So let's say we need a critical value for a 90% confidence interval. That z-value is 1.645. So what this means is that if we have our normal model, let's draw this out. So standard normal, we'll put 0 in the middle there. Remember that the standard deviation is 1 for the standard normal model. And about here and here, and -1, +1, you get your cutoffs. So with a z-score of 1.645, we go out about 1 and then about 2/3 of a standard deviation further. So right about here, 1.645. This number right here, along with a partner down on the other side, -1.645, these two values are going to cut off the middle 90% of this normal model from everything else. Now, specifically when we talk about critical values for confidence intervals, this 90% will always be centered. So if we drew a line down the center right here at 0, 90% of your area goes in the middle. So that means that this half is 45%, and then this half here is also 45%. Now, if you keep doing a little bit of math, here's 100% of your data, or 100% of your area. If there's 45 and 45 in each of these little sections, or these big sections, then that means that these sections shaded all the way on the right, and then this little tail over here on the left, each one of those is going to have 5% of the area. So this one also gets 5%. When we're making confidence intervals, we're trying to have some symmetry around the center number. That's why we put 90% area in the middle, or maybe if you're doing a 95% confidence interval, you'd put 95% area in the middle. Either way, it's always going to be symmetric. So you're always going to have this pattern of 5% and 5%, or maybe it's 1%, 1%, or 0.5%, 0.5%. So this critical value, sometimes we call it Z star. Some textbooks use Z star to tell you, hey, this is a critical value, 1.645. Some textbooks use a different notation, Z 0.05. And I've filled in some numbers here. Generic version is Z sub alpha over 2. So let's get back to this Z.05. This 0.05 tells you that there's 5% in that upper tail. So I'm going to highlight 5% matches with this 5%. And coincidentally, there's 5% in the left tail as well. But we want to have a positive value, so we're always saying, hey, the 5%'s in the right side so that you get your positive critical value. If you look at a confidence interval formula later on, there's a plus and minus. So the minus on the left side is taken care of. You just want the positive right now. So back here, Z.05 is 1.645. Now this alpha over 2 is a way of saying that we can put alpha area and then divide it by 2 in each tail. So in this case, alpha would be 10 because 5% and 5%, that makes 10%. And then when you go back and divide by 2, you get your 5. So it's telling you want this much area in your tail. So how did we find 1.645? I'm going to do this on StatCrunch. I'm going to go to Stat, and then calculators, and then normal, because we have a normal model. Now, conveniently, there's a between button. So we can tell the calculator here to say, if our mean is 0 and our standard deviation is 1, find these two numbers here so that this area, this probability, this percent, is 0.90. And then push compute. And it gives us negative 1.6449. So that's this cutoff here between the red and the white regions. And then there's the right side as well, 1.6449 out here. So this calculator used a lot more decimal places. It bounds this 90% area by negative 1.6449 and then the positive version. It goes out to 4 decimal places. Some books round sooner or later. If you go out to 3 decimal places, you can see how it's 645, 645, just like I was using on that document over there. Some textbooks will round a little bit even more and say it's 1.64, plus and minus 1.64. And that's okay. This is just being a little bit more precise. At least use 2 decimal places. 90% is so common that 1.645 gets used often because it's just common, so it gets used. But 2 decimal places is the absolute minimum of what to use. So let's go back here and look at another example. The critical value for an alpha equals 0.05 right tail hypothesis test is z equals 1.645. So this is a little bit different use. If you're just learning about confidence intervals, this stuff won't make sense. If you've already learned about hypothesis testing, this will make sense, and then that previous example will have been review. So this is another use of a critical value, but when you're doing a hypothesis test. So the hypothesis test is told to be right tail, so I draw my normal curve, standard normal. This alpha equals 0.05. On this right-sided test, it's telling us, hey, on the right side of your normal model, we need to put in 5% area. So this ends up being this 0.05. Sometimes this is called a rejection region. Rejection region. Sometimes this is also called a critical region. The idea is that in a hypothesis test, if you get a test statistic that lands far out here and lands in this 0.05 rejection region, we end up rejecting our null hypothesis. So 0.05 was that alpha value, and it was all on the right side, so that's why I drew it over here. 1.645, this is the z value that cuts off 5% from the other 95%. I'm just lumping it all together, the other 95%. Now, I chose this problem purposefully because 0.05 on the right side, if we pretend, so I'm going to pretend, I'm going to write it in yellow so we can't really see it. If we put 0.05 on the left side, see how it matches up to the last picture? 5%, 5%, 0.05, 0.05. I'm going from decimals to percents, but they mean the same thing. If I pretend that I had 5% over here on this left side, then that would reduce the middle area to 90%, and then it matches right up to a confidence interval value. So there's going to be a lot of similarity between certain hypothesis tests and confidence intervals. You're going to run with the same numbers. So back earlier in the class when you learned about finding values on a normal distribution, that was in preparation for finding critical values for confidence intervals and then critical values for hypothesis tests. So let's find this 1.645 on a calculator in StatCrunch. I'm going to go back over here to the normal calculator. I'm going to choose standard, and I want x greater than or equal to some number. I want that area in the right side. That's why I choose greater than. Mean of 0, standard deviation of 1. It says find me the x value where if I go above that x value, I'll get 5% of the area. So I put in 0.05 and it gave me 1.64, and hey look, we have more decimal places now. You could round that to 6.4, 6.45, and that's probably good. This many decimal places is a little overkill. If you had a left-sided test, I would just switch it around. Less than or equal to some number would give me 0.05. Push compute again. See how it gave me the negative sign? I just flipped it to the opposite. It's that mirror image because we have a symmetric distribution. All right, so the critical value in that problem was 1.645, and I chose that because it was really similar to that critical value problem. Same kind of numbers, it's just sometimes we focus on the area in the tail, sometimes we focus on the percent in the middle. So lastly, find the critical value for a 99% confidence interval. And oh, I've already calculated it, it's 2.58. So let's draw a picture of what this means. Not in yellow. We have our normal model. Mean of 0, 99% confidence interval. That means I'm going to be putting 99% area in the middle, so 0.99. So if I shade that, here's my 99%. On StatCrunch, I'm going to go over there now, between, if I want my area to be 0.99, these spots empty out, I put my 0.99 over there, mean of 0, standard deviation of 1, and here's my critical values. There's a -1 because we have a cutoff on the left side, negative 2.5758, and on the right side, 2.5758. So you can see how that rounds to 0.58, negative 0.58. You can also use 576 if you want to go out to 3 decimal places. Just some options there for when you're working by hand. So StatCrunch, we kind of confirmed that 2.58 is that value. Oops. So Z equals 2.58. Usually when we talk about critical values, we only give the positive one because the negative one is implied. It's implied in the formula for the confidence interval. Here's a negative 2.58. That's the Z value. If we ended up using a normal table to find this value, it takes a little bit more work, and you have to focus on what area is in the tail. So you just don't look up in the table 0.99 and then let's draw out a table here. So if this is a normal table, you wouldn't look for 0.99 and then go up and find your 0.0 something and then go to the side and find your 2 point something. The 99 is the area in the middle. So we need to focus on areas in the tail because the normal table only finds area to the left of something. So let's do a little bit of math here. If there's 99% in the middle, well, there's 100% in the table. So we have 1 minus 0.99. That is equal to 0.01. So that means there's 1% area in those two tails total. But since I have two tails, I need to take the 0.01 and I need to divide it by 2. So this is where decimals get a little tricky because we have 0.005. And this tail as well, 0.005. So when you go to a normal table and try to find those critical values, you're going to be looking up either 0.005, and make sure to not look up 0.5 or 0.05. Get enough decimal places in there. Then you'll slide to the side and find the negative 2.5. Then you would slide up and then you'd find about the 0.08. Now this is not exact. You might be somewhere between the 07 and the 08, but again, you can just kind of round and pick one of those that's kind of close. Now, why did I choose 0.005? Well, it's a smaller number. It gives me the left side. It gives me the left critical value. If I wanted to find the right critical value, when I look at the table, I would have to be looking up 0.995. So think about this. If I want a positive value, I need to find all this area all the way to the side. That's the 99% area plus the 0.005 area, so it makes, add those together, 0.995. Then when I slide out to the side of that normal table and slide out up, I'll get positive 2.5. And then I'll be looking at the 0.08 column, and that's how you get the 2.58, or split the difference, 2.575. That works as well.